Okay, in the last video, we showed that if you've got a redox reaction, with the case we had zinc metal, copper ions goes to zinc ions and copper metal displacement reaction. Well, we could actually in our head separate it into two half equations first of all, and those two half equations I've shown them as reversible equilibria, that one and that one, and then you could actually physically separate them by putting them in two beakers like we've got there. And you would find in this case, well, that you put a voltmeter there, you'd find that you get a voltage of 1.1 volts, and the copper would be the positive electrode. That's always the one on the right hand side. So that means the electrons will be flowing from the negative. Remember, electrons are negative, from the ground in that direction. Okay, and that showed us that, well, if we look at this half equation, it shows us that if we think about the potential oxidizing agent there, the potential oxidizing agents in those two reactions, well, is copper 2 plus, because that's potentially going to take in electrons, and zinc 2 plus. And copper was the best oxidizing agent because that was the one that actually did take in the electrons. Or you could look at it the other way. You could say that the copper and the zinc are potential reducing agents, and the zinc was the best reducing agent because that's the one that did give away the electrons, push them around. So we've got two half equations there. Now we know, and they're all metals and metal ions, but we know loads of other half equations, redox half equations, that don't involve metals, and we could do the same sort of thing with them. So let's think about if we got iodine. So we've got I2 and 2 electrons can go to I minus. Well, could we set up a beaker like that? We could. What we'd do is we'd get a beaker, and I put in the iodine in solution, and also some iodide ions, and probably potassium iodide. And then we'd get the salt bridge connected up. That would go to our zinc side. I'm going to swap the copper for the iodine here. But then we've got a problem. What would we connect it up to? Well, the answer is you would use a piece of platinum. Okay, so that's a piece of platinum. And the reason why you'd use platinum is because it's very unreactive, so it's not going to start reacting and mess everything up. Okay, and you'd have your wire going out. Okay, now, so you could do that. And if you remember the little cell diagrams that we did, rather than say we're drawing all these pictures, how would you represent that in a cell diagram? Well, you'd have the iodine would still be the positive one, so that would be on the right. You'd put your salt bridge there like that. You'd have your zinc on the side, the zinc 2 plus, because that's the oxidized form of this equation here. Phase change, and you have the zinc, that's the reduced form there. Then on the other side, well, we need to look at this equation. The oxidized form is iodine, so we have I2 there. And the reduced form is I minus. Now there's not a phase change, they're both in solution, so you just put a comma. But then to show this platinum bit here, you do that and PT, and you would have a line there because it is a phase change, because platinum is a solid, the other two in aqueous solutions. And if you did that, you'd find that the E for that cell would be 1.3 volts. Sorry, 1.3 volts. And that is a little bit interesting, because it suggests, look, the voltage we got when we had copper there was only 1.1 volts. So that suggests that I2 is better at accepting electrons. E minus than copper 2 plus. So that means we've done a measurement. We said that iodine is a better oxidizing agent than copper 2 plus, and we can say it's better by 1.3 volts minus 1.1 by 0.2 volts. We can say that, a little calculation. Let's think about another half equation we could put in there. Right, let's swap this again. Let's swap the copper one with, well, you might be familiar with this one. You probably are. Depends if you've done transition metals yet. Manganate ions. So that's your dark purple ions, and you need it to be acidified. That's a pretty strong oxidizing agent. do it as a reversible, and that's going to go to Mn2 plus and 4H2O. So let's see, what would we do there? Well, we'd have a little beaker of, right, what we'd have to put in there, we'd have to put manganate ions. So this would be a nice purple color. We'd have to put in there some hydrogen ions, and we'd probably add some sulfuric acid, yeah. And then we'd need the reduced form, which is Mn2 plus. We need some Mn2 plus ions in there to set up this whole equilibrium. We need to set a whole reaction there. And then we'd need, there's no metal there to conduct, so we need a piece of platinum in there as well. Okay, and then we'd have our salt bridge there connecting up to the zinc. So let's draw a cell diagram for that one. So the manganate is the most positive one, so here's that will go on the right. So here's my salt bridge. Right, manganate equation. What's the oxidized species? It's MnO4 minus. We don't have to put the H plus in there because the hydrogen doesn't change its oxidation number. It stays in +1 throughout, or the water, because there's nothing happening there. Then the reduced form is Mn2 plus. That's got an oxidation number of +2. Manganate +7. Then we'd have to show our platinum with a phase change and PT, and then we just have the zinc on the other side like that, as usual. Okay. Now, when we did the E cell of that one, you would find that that is really a really big voltage. That is plus, right? I should have said plus there as well. Is 2.30 volts. So you get a much bigger voltage when you use the manganate compared to the iodine. Yeah, the iodine is 1.3. It's a whole volt better. So that tells us that the manganate is a much better oxidizing agent than the I2. And we can say it's better by a whole volt. Now, you can probably see now it gets very complicated. If you just keep comparing pairs of things together, it'd be very hard to put them all in an order. So what people said was, let's compare everything to one electrode. Let's call that one 0, one reaction. Let's call that 0, and see how everything compares to that. Now, the reaction they chose for that was the redox reaction was H2 plus 2E minus goes to H2 gas. Sorry, that should be 2H plus, do beg your pardon. So 2H plus, 2 hydrogen ions plus 2H goes to hydrogen gas. Right, now, how could you set up a half cell with that? And it would be quite tricky because you've got gas involved there. Well, I'll show you. This is done. I've got drawn it down here. You can see there. What you've got is you have this glass tube here, and it's got little holes in it at the bottom there to let the hydrogen out. The hydrogen comes in at 1 atmosphere pressure. That's important. If you increase the pressure, you'll change the voltage. Yeah. You have a platinum wire. Sorry, that should then connect to the other half of the cell. And at the bottom of this, you have this finely divided platinum, which is catalytic and helps the hydrogen ions and the H2 exchange the electrons. And then that's just the salt bridge. Okay, so how do you show that on a diagram? Well, you show it like this. There's your salt bridge, and you put H plus here. That's the oxidized form. Phase change, because of the reduced form hydrogen is a gas, and that was an aqueous solution. And then you knew the phase change, and you've got platinum, PT. Okay, so you compare everything to that. Now, I've got a whole list of things here, and these are called standard electrode potentials. And what this means is, let's say I connect the zinc one up to that. So I have Zn2 plus there and Zn, right? With a standard height, this is called a standard hydrogen electrode. You always connect that on the right-hand side of the cell. and then the reading of the cell that you get here. In this case, it's going to be minus 0.76 volts, and that shows you that the zinc is more willing to give away electrons than the hydrogen. Right. So let's have a look at a load of these values. I've got them here. Oops, sorry. Okay, so you can see that list there. I'll just zoom in a bit so you can see it better. Right. Right, you've got a whole load there. Okay, I'll shrink this. Now you can see hydrogen. I've done that in green there. So the other example I gave, the zinc. Right, so here's zinc. Yeah. So, and that's minus 0.76 volts. That means that would be the voltage of the cell if you connected the cell, if you had your hydrogen on the right hand side and the zinc would be on the left. If you connect that cell up, you get a value of minus 0.76 volts. Likewise, if you did the, let's say the iodine one, which we talked about before, if you connected that up, so you put your hydrogen on the right, and you'd put the iodine on the left, so that'd be I2, the reduced is I minus, and you would need platinum there. If you did that, you'd get E cell for that would be equal to 0.54 plus 0.54 volts, okay? So that's why you get 0.54 volts there. And of course, this one here, if you connected it to itself, you get a reading of 0 volts. Now, these are indispensable, really. Very briefly, let's have a look. This one, the bottom here, potassium, that's the most negative. So that means that's the best at pushing away electrons from itself. So that means K, metal, we know that it doesn't really like being K metal. It wants to lose that electron. It's very good at pushing electrons away. And if we look at the other side, well, on the left-hand side, all these things have, on the left, they will have some tendency to accept electrons. In the case of K plus there, it's got a very, very low tendency, as we know. It doesn't like turning back into potassium metal. Whereas if you think, what do you guess would be at the top here? Well, you might think, what element likes electrons the most? Well, it's fluorine, okay? Fluorine, F2, it loves electrons. So it's got a really positive value of E, of the standard electrode potential. And that we give that little symbol there, E, standard sign, yeah, and it's measured in volts. Now, if you draw any cell at all, so let's choose, shall we choose chlorine and bromine, okay. So if I did that, I'll zoom in here a bit, I think. Right, we've got chlorine and bromine, we can see them there. Right, so we're looking at this one and this one. Right, so if I connected a cell up there, there's my my salt bridge. Which is the most positive? Well, it's the chlorine, so that goes on the right. So I'll put Cl2, no phase change, aqueous solution, the chloride ion, and you would need platinum for it. On the other side, you need bromine, that's the oxidized form, Br minus the reduced form, and platinum there. Now, if you worked out the, if you wanted to know the E cell value for that, so if we connect to that, what would be the voltage reading for that E cell? The rule is what you do is you do E right minus E left. What is E right? It's the chlorine value. Well, the chlorine standard value, these are the standard values, electrode potential. Well, it's 1.36 for chlorine, minus, and it's plus 107 for bromine, sorry. So that answer there would be 0.29 volts. That would be the the value of the E cell there. And this is quite important. They always ask you to work out E cell. They'll give you two physical half cells, yeah. Stick them together to make a full cell and work out the voltage of the full cell using that equation, right minus left. And of course, they give you a whole table of values like this to be working with. Okay.